Hello, everyone, and welcome to today's Open Teams community event. I'm Brian Skin, the Open Source Architect Community Manager here at Open Teams, and I'll be your host for today. Open Teams is the single point of contact, procurement, and accountability for a network of experts and complementary services ensuring your success with open source. Visit openteams.com or reach out to us at connect@openteams.com to learn more. As part of Open Teams' overall mission to sustain and support open source, we are sponsoring the Open Source Architect community with the goal of providing a dedicated space for experts to connect and collaborate over their favorite open source technologies. To learn more or to apply for membership, visit openteams.com/OSA-community. We are also sponsoring the Engineering Manager community on LinkedIn, focused on fostering the career and personal development of engineering leaders. Visit openteams.com/EMC-LinkedIn to check that out. Today, we have a roundtable event for you on the topic of vectors and embeddings. Large language models, LLMs, have received a great deal of attention over the past year since the release and meteoric rise of ChatGPT, along with others, similar applications and other variants of generative AI. Vectors and embeddings are a key technological component of any AI or ML system that interacts with text, serving as a mapping between that text and a numerical representation that the models can understand. In this conversation, the plan is to focus primarily on a subset of this broader topic area on approaches and technologies for storing, searching, and visualizing vector data sets. Really looking forward to it, and I hope everyone in the audience is too. Thank you for being here. We are open for questions. Please send any that you might have into the chat. We'll address as many as we can in the course of the conversation or at the end. We are recording today's event, and that video will be posted on the Open Teams YouTube channel once it's once it's ready. Subscribe there to be notified when it goes live. Okay, that out of the way, let's get started. Hello, panel. Welcome. Really excited to have you here. We've got a big audience. Hopefully, we get lots of good questions. Welcome.
Thank you, Brian.
Great. So let's get started by letting the four of you introduce yourselves. We'll just go clockwise on my screen. Andre, how about you start?
Sure. Hi, everyone. My name is Andre. I'm a founder and CTO of a company called Nomic. Basically, what we do is we really care about explainable and accessible AI, and we build systems that help support it. So one of the things that we really focus on is how people can interact with unstructured data nowadays. And sort of the core way to do it is through embeddings. So that's why we're here.
Excellent. Lawrence, you're next.
Hey everyone, I'm Lawrence Ondermaten. I'm a research scientist at Meta AI. I've worked in the machine learning space for over 15 years on a variety of different topics. First as faculty member at Delft University of Technology, prior to that at UCSD, as a postdoc and currently at Meta. And some of my, I would say sort of all of my work has used vectors and embeddings throughout in sort of a previous life for visualization of embeddings through a technique I developed called T-SNE that maybe we'll talk about later in this session. But more recently, as part of the Llama team building multimodal foundational models.
Excellent, thank you. Ben.
Hi, I'm Ben Schmidt. I'm the VP for Information Design here at Nomic. I have a sort of circuitous route into software and AI. I have a history PhD and I was a history professor for several years, but working with data in a field called digital humanities, sort of saw my research practices transformed by the emergence of huge digitized data sets like Google Books came out when I was in graduate school. And it was clear sort of from the beginning that these new representations of massive collections of data where people don't know what's inside of them were going to offer really important and transformative ways of interacting with, understanding the various sorts of data collections that people work with. And I was doing a lot of work, especially with techniques for in-browser data visualization on some of these two-dimensional models of them, like the ones that other people here developed. And then I came to Nomic about a year ago to help figure out how to help other people do that kind of work too.
Excellent. All right, Leland.
Hi, I'm Leland McInnes. I'm a researcher and mathematician at the Tata Institute for Mathematics and Computing. And my work in data science has been research on clustering, dimension reduction, and approximate nearest neighbor search, things like that. I'm very interested in unsupervised learning in general. And so embeddings and vector representations come up all the time. That's how these unsupervised techniques are how we can actually explore these very large data sets of otherwise unstructured data. If you provide embeddings, now you can work with them with all these sorts of tools in the unsupervised learning toolkit. So have been for a long time very interested in what we can do with embeddings from that point of view.
Terrific. All right. Welcome to all of you. Thank you. So let's dive in. Vectors and embeddings. So I see, I see my role here. I have a chemical engineering background. I've been the developer in various ways for a while. So I personally know what a vector is. I know the idea of what tokens are and words are, and the embeddings go from one to the other. But that's about the extent of it. So I'm looking forward to to all that you have to say. Where is a good place to start? What is an embedding? What are the vectors? They're necessary so that the deep learning models at least can address them. Just a quick reminder of why are they so important?
Yeah, I can start out with that. Give sort of like a layperson sort of definition and explanation of like what the object is, and then I'll let the smarter people in the room maybe build on that a little bit. So generally when computers sort of send information to each other, they're sending around sort of like ones and zeros, like bits. And if I was to go and like, take a sample from the wire running out of your house of just like a stream of information, I'd get all these ones and zeros. And those ones and zeros may represent an image that's being sent, a Netflix video that's coming across. It might be some book that you're shipping over. Hopefully it's not the books 3 corpus or something like this, but it might be some book you're shipping over. And you never know actually what that information represents, right? You need all these like fancy sort of file indicators for a computer to know like what type of format a file is and what kind of information is contained in it. What an embedding allows a computer to do is instead of sending sort of bits of information that sort of like are independent of each other and you kind of don't know what the computer can't really interpret what that means, it allows the computer to communicate over with meaning. So if I was to, for instance, send an embedding of a piece of text, that computer would be able to interchange that piece of that text for the meaning of the text, and so on and so forth. For, let's say, if I was to send an embedding of an image, so an embedding allows a computer to sort of communicate with other computers, but exchange meaning as opposed to just exchanging sort of bits of information that might not be discernible if you don't have context around it.
So, like, for example, if the word house were being sent over the wire under a conventional computer processing modality, it would be characters, HOUSE in English, and you'd have that information, and it'd be up to a human on the other side to be able to parse that. Whereas in an embedding, you might have ideas of the idea of home, the idea of a structure, the idea of perhaps family, those sorts of things in that numerical representation.
Exactly. Yeah. Yeah. But to build that numerical representation, you got to do a bunch of fancy math beforehand. But yes, once you have it, that's what you get.
Great. Any other thoughts there for the rest of the panel?
Yeah, I think one important thing to keep in mind is that there's nothing inherent in the single numeric representation vector. So if you have whatever model you want spit out an embedding of house, that's just a vector. It's just a bunch of numbers. It by itself doesn't mean anything. What matters and makes this valuable is the relative representations of all the different other concepts. So when you embed get the vector for family, that will be closer to house than the vector for banana and airplane. And it's this relative representation, the geometry of where these different embedding vectors land relative to each other that matters. So different embedding vector models will spit out entirely different looking vectors for the same input. And that's fine because relative to the other equivalent related terms or images or what have you, they preserve some notion of closeness. And so the embedding models are about defining what it means to be similar and what it means to be different. And that's what you're encoding into this embedding, is the relative comparisons between the different objects.
Is there any analogy there to human language? For example, again, using house, Spanish, you have casa. A string of characters, that letter vector, so to speak, is very different. But because the languages are different embedding models, so to speak, what they produce is different, but they have the same semantic meaning.
Yeah, that's pretty similar. I mean, a lot of the word embedding techniques from back in the day are very much related to looking at what other words occur around a given word. So in a sense, you can create counts of how often this word occurs with other words in all the possible sentences that might use the given word. And that's a really long sparse vector, but it's still a vector representation. And in fact, a lot of word-to-vex representations of words are essentially this, just compressed down to be dense vectors. So in the same way, casa and house are going to be used in similar ways in sentences, just with different sets of equivalent words in English and Spanish. So the representations relative to the other concepts are all going to be similar. And so you're going to end up providing similar relative representations.
That makes sense.
Yep. Yeah, one cool thing to add here, I think, is one thing Leland mentioned is nowadays when you think about embeddings, people usually have this idea of this like output of some sort of neural network that was trained specifically for, building a representation of an object, a piece of text, an image, or whatnot. Before, 2013, 2012, before I would say Word2Vec, people didn't really think of it in this manner, especially if you weren't working in the neural network space, I think. Which I guess most people here actually were in this panel. But the traditional techniques for building sort of like representations of, I guess, text is where this sort of idea started out, as it was just very hard for computers to interact and to kind of communicate with text in any sort of like form that wasn't just like the raw characters, the raw bytes encoding the text, was to do these sort of like simple sort of like count-based statistics. How do you represent a document? You can represent a document by weights relative to the sort of like unique words that occur in the document, to this sort of thing. A lot of traditional like search and ranking algorithms nowadays actually still rely on these sort of like basic statistics to be able to like have their like high performance and like retrieval tasks. This is when you see like a vector database or something like this, when they mean hybrid, they usually mean some ranking system that's based on these sort of like more these kind of like older statistical methods for building representations and embedding specifically text to be kind of augmented with the newer stuff that's come in past like 2012.
Cool. Detail question: how in the actual practical implementation, how long is a typical, if there is such a thing, a typical vector embedding of something? Is it hundreds, thousands of elements, or?
I mean, it varies a lot. I'd say, in the thousands typically.
Okay.
Like, I mean, at least if you look at sort of like modern large language models or things like that, sort of the representations are of that size. Something that is important to keep in mind is that, sort of like one way to think about these representations is as, sort of like lines or points that live in some high dimensional space, and high dimensional spaces are very weird things. Sort of the, maybe if you take anything away from this webinar, like take away that, like you don't have a good mental model of what a high dimensional space is. And that includes, sort of the experts here in this panel. We do understand some like things about these spaces, right? So for example, like, and you can easily sort of confirm this mathematically, like if you put an apple, like if you have an apple, it's a three-dimensional thing, right? And most of the volume of that thing is going to be like in the fruits, right? And there's going to be a tiny little bit of volume in the skin, right? But it's almost nothing. If you had a 1,000-dimensional apple, so you just sort of blow this thing up, in the same way that you go from a circle to a sphere, you can go from a sphere to like some 4-dimensional or 1,000-dimensional spherical object, right? So you can imagine a 1,000-dimensional apple. All the volume will be in the skin. And there are sort of lots of, sort of different things like that are very counterintuitive for us as humans with our like three-dimensional, sort of world representation that we are used to. And so the main thing to take away is like these spaces, they're very counterintuitive and they're very large. And because they're so large, they can represent really, really rich things. Even though you think, well, what can you really represent in like 1,000 numbers, right? Like, can 1,000 numbers contain meaning? And they can, right?
Yeah, so that I think starts to touch on one of the vector search topic that we'll get into. Is you have this large complex object telling what's inside and what's outside starts to become challenging because you run into things like non-convexity and those sorts of things, I would guess. So yeah, we'll get there. All right, so let's, I think a lot of the people with the interest here probably know this, but let's talk a bit about what does AI do with the vectors once the embeddings have acted on the text? Just the framing, how do deep learning models work, neural nets, et cetera, just to make sure we have that mentioned.
I can give the super, well, I'm tempted to give the super rough explanation, even though Lawrence could give a much better one than but maybe I'll let Lawrence do it. Actually.
No, go for it, Ben, go for it.
I will say, so one of the things that I would say is that basically every machine learning model is a model that produces vector representation, that produces embedding representations of things. Just some of them then use those vector representations to do something else, like to predict the next word in a sentence or to predict a classification for a photograph. And what happens is that you take any of these different data sources that exist in the way that we conventionally digitize things. You take a photograph and you turn it into a bunch of red, green, and blue pixels in a particular shape, or you take a text and turn the text into a list of words that you can start off with embeddings for them. And then you pass that through a set of matrix multiplication operations, basically, which have become a lot cheaper recently, thanks to GPUs. And after you've done between 2 and I don't know how many you can get up to nowadays, a few thousand matrix multiplication operations, you come up with a new representation of that thing in the high dimensional space. And if it's an embedding specific model, you've got something which is just supposed to be a representation of that text or of that word or of that image too, because these are not specific to text. And that's one of the areas which is really interesting. And some of the people at Nomic have been doing a lot with recently is that you can put images and text in the same space in a way that you couldn't before. But sometimes those embeddings are just the penultimate layer before the machine learning model does what it really wants to do. But embeddings are fundamental to every kind of AI model that exists right now because they're the sort of lingua franca that are used internally to represent things before the final task that we're using it for.
Even the ones that aren't generative AI. I mean, you mentioned like the sparse, the one-hots, the
one-hots where you're trying to do classification,
Yeah, I mean, the general word that I like to throw around is like this idea of like compression. So like deep neural nets, they're really good at finding like salient patterns in a large collection of data and finding all the things that are the same across disparate data points in a data set and distilling that down into sort of a compressed representation, right? In the very same way, if I take like a 1,000 by 1,000 pixel image, right, with 3 dimensions for like red, green, blue colors, for example, that is in some sense a representation of that image, just a representation of that image that's very, very hard to work with and is not comparable. For instance, if I take, let's say, like some sort of similarity metric between the pixels of an image and the pixels of another image, there's going to be a lot of dissimilarity between those two things. But the representation of that image through a neural network, which has been passed through to sort of extract out all those patterns that it can find across a data set of images and kind of the distilled parameters. Now I can begin sort of applying ideas around closeness, like Leland was mentioning, that now become actually applicable, which becomes really useful downstream if you care about, pulling out the salient information out of the image and not just like, what is the main color in my image data set, which is probably what you would get if you were looking at just like the pixels, for example. just to stay on the topic of images there. Maybe this is actually a great place for Leland to maybe add in a little bit. You were really emphasizing this idea of just like relative distance, and that's actually what matters at the end. I think this is exactly what we're talking about.
Yeah, so I mean, I actually am not the expert on neural networks, so I'll be happy if Lawrence would provide further details on that. But I will talk to the notion of embedding as that relative distance. My simplification as a mathematician is you're just applying a lot of transforms to generate this notion of closeness that matches the notion of closeness you need for your task. And so each neural network is going to have some task in mind, be that predicting the next word, so you can do generative text, or image classification, where you want images of similar objects to end up close to each other, so you can predict that they're the same image class. So it's really just about twisting the space around in such a way that you encode a meaning of closeness that matters for you for your task. And so each different model is going to have a different notion of what's important to have things be close or similar.
Makes sense. All right. I think that's a solid intro on vectors and embeddings generally. Let's move to the first specific topic that we had in mind, vector databases. Because in order to work with data, you have to have a place to store data. So we need to have some place to store our vectors. I'm familiar with SQL and NoSQL and kind of the more traditional database styles. And I know of vector databases and that they are purpose-built to store and retrieve vectors. Why do we need that? What's different? Is it because the vectors as objects are so large? Is it because of how we need to search for them? Why do we have different technologies for storing vectors?
I mean, I can maybe kick us off and then others should weigh in. I think, sort of a key difference between vector databases and traditional databases is that in traditional databases, when you do a query, you're sort of looking for exact matches, right? It's like things that fall exactly in the range that I specify for a particular column or sort of things like that, right? But vectors or sort of vector representations, they're a little bit different, right? Like they're not sort of typically discrete things of the type that you would see in most traditional databases, and so you're much more looking for, as Leland put it, for sort of things that are similar. Right? It's like, sort of, I have a particular query, I represent that query through some vector embedding, and now I'm going to use that vector embedding to query my database for similar embeddings that are then linked to sort of like underlying data, right? Like those embeddings were created in some way, they're associated with some underlying observations, and those are the things that I want to retrieve, right? And so the way that the search or that the query is going to work is basically I'm going to have to scan through everything that's in my vector database to find the things that are similar, right? And then sort of like the key sort of piece of technology that these vector databases provide is they provide techniques to make that search really fast. Because if I'm going to scan through, sort of like billions or trillions of let's say posts on social media, sort of relevant, I guess, to my employer, right? You don't want to do a linear scan because you're going to be waiting for forever, right? And sort of that piece of technology is sort of what makes vector databases unique and really quite different from the more traditional relational databases.
Yeah, Lawrence kind of hit the nail on the head there. It's really that sort of indexing operation. The very same way in a traditional database, you have a column, you can create an index, and maybe if the column's like a short string of text, you can have an efficient index to search over that. A vector database allows that column to be a vector or an embedding, and they have sort of most of the algorithms are actually pretty old now. Vector databases, the idea has been around for a while. Things called approximate nearest neighbor searches, approximate nearest neighbor indexes are the indexes that you build in a vector database. It's just that for the context of the kinds of applications that people use nowadays, like it's the kind of question I get a lot is like, what vector database do I use? Because it seems like there's a new one popping up every day. If you go to like San Francisco and you drive down the highway there, you see a different vector database on the billboard every few miles. And everyone's like, what the hell's going on? Like, what do I do here? What's actually different between them? At the core technology level, the answer is like not that much. A lot of it is just like how you're able to go about actually productionizing these things. What are the trade-offs you need for your actual use case? And that's the core differentiator that you have. Is the vector database open source, right? Can you stand it up on your own infra and not have to rely on somebody? Well, a lot of people don't realize this nowadays still, and like you always see this sort of a joke on like social media floating around. It's just like you generally don't really need to even use any sort of managed vector database if you have less than a couple 100,000 embeddings or a couple 100,000 vectors, because you can do that in memory pretty quickly, for example. So like it's a way to manage vector search or similarity search. That distance computation that's ultra important to all interactions you do with embeddings, that computers have to execute quickly to be able to assess this idea of meaning that I was mentioning earlier.
Indeed. Ben, you had something?
Yeah, I was just going to follow up on what Andre was saying, which is that, like, I think it's important with the technologist audience to be clear, like, a lot of people don't need vector databases that are using vector databases. If you're trying to do nearest neighbor search across 1 trillion things, because you have 1 trillion social media posts, like, you absolutely do need these kinds of indexes built up. But I think one of the things that we often see and that I hear about some of these vector database companies is that the size of the vector sets that people put into these are sometimes not so large that the fast retrieval of nearest neighbors is not something you could just use with NumPy. Like, it's actually relatively quick, even in the realm of like a few million points to just do it yourself. So you don't necessarily always need one of the vector databases just for the nearest neighbor operations. And that's one of our value propositions, honestly, is like at Nomic, we're trying to provide ways of actually understanding the vector spaces as opposed to just stuff that you do in that you can do with matrix multiplication operations.
Mm-hmm. Yeah, I'm reminded. I'm gonna have to paraphrase it, but not just about vector databases, but a lot of technologies in general. There's do you need this? You're not Meta, you're not Instagram, you're not Netflix. You don't need this complicated, fancy thing, or high featured thing. Try the simpler, easier, more accessible thing first, and maybe that will work just as well for you.
Yeah, I mean, there's several angles to it. Just like I don't want this to turn into like vector databases are useless, because they're not. There's a whole lot of developer experience that comes into it as well. There's other angles than just like, the math is the same across all of them. The operations are the same across all of them. It really comes down to like, what does the developer community want to use, right? Because like, I think this year has been really interesting. Like, the whole reason we're even having this like embedding roundtable right now is because this year is where like AI in some senses went mainstream to the software development world. It's the first time where software developers and software engineers who didn't really know about machine learning got the chance to kind of use the technology and work with it. And I think kind of it's been really instrumental to see that like some of the existing players, and specifically like the vector database world, didn't actually win when that happened. The players that provided the best developer experience at companies like Chrome or companies like Weaviate in their actual offering were the ones that people chose to use, even though the technology under the hood is like maybe relatively the same across all of them. So that's maybe an interesting point to add in here.
I forget where I saw it. There was an article or a blog post I saw recently. There was actually, from what I took away from it, was making the case that even the conventional, the well-known like SQL database names, MySQL, Postgres, and stuff, are adding features. They're actually adding on to the projects are adding on features that make them at least a better fit for vector applications. Kind of narrowing the gap even further to blurring the line between a conventional and a vector database, at least for some applications.
I think, as others have said earlier, it's really just about the indexing. So in a traditional SQL database, you might have like B-tree indexes for fast search. If you can add another index type that can index these vectors, that's all you need to be a vector database. So if these other database solutions add these other indexing solutions, that suddenly makes them capable of handling vector storage as well. So it's really about the difficulty of adding that kind of index. And a lot of that is down to, as Lawrence was saying, high dimensional space is just very weird and very non-intuitive. And the things you would think to do if you want fast search as opposed to just scanning everything are actually hard to get right. And so this is where there's maybe a little more subtlety, is in exactly how to build those indexes. That's what the vector database companies are taking care of for you. They've already built all the algorithms for how to do that, and they're trying to do that quickly for you. And so I presume these other standard SQL databases are picking up some of the same sorts of algorithms. I will say, as somebody who I have developed approximate nearest neighbor search libraries, there's a lot of tuning involved in actually getting the performance out that can be claimed. To actually tune exactly how the approximate nearest neighbor search works, even for any of the algorithms that these vector databases use. And in some ways, I would say that's still one of the hard parts. And that's maybe a thing you want to look for from vector databases if you're shopping around, is how easy is it to tune, and you actually want to do benchmarks to verify that, and how much support are they going to give you in managing to do that, because it can be more challenging than you think to get the full level of performance. If that's what you really need, if you really need that really fast search, getting that level of performance for your data is trickier than you might imagine at first.
Makes sense. Excuse me, makes sense. From another aspect of, it's not exactly performance, but storage efficiency. So they're dense numerical vectors. Is there any do any of the vector database offerings as a quantization, perhaps? Yeah, like how do the various the tooling to reduce size, increase calculation performance, etc. Is that a thing that the vector databases tend to have built in or have accommodations for?
Yeah. So I'll add this, then I'll actually give it off to Lawrence, whose company maintains one of the best libraries for doing exactly what you just said. It's called Face. So yeah, like in general, when it comes to vector databases and vector search, it's always a trade-off, right? It's like, depending on what your downstream use case is, and exactly like Leland just said, depending on your data set, you want to do a lot of tuning. And if you, for instance, care more about, like, for instance, metrics like a recall versus metrics like queries per second you can execute in a fixed like unit of time, like how fast you can actually retrieve your vectors, there's all these different trade-offs you can do. So quantization is just like one of these dimensions of trade-offs where you can get increased speed in exchange for like decreased performance for some definition of performance. And yes, sometimes it boils down to things as simple as like chopping off bits, but oftentimes you have to be a little bit more clever about, like, how you go about chopping off bits, and maybe you bind together similar dimensions in your embeddings by doing statistics across your entire embedding space, for example. But Lawrence has probably built much bigger vector indices than I ever have. So maybe
I don't know that I have. But I think Andre, captured it really well, right? Like, quantization is sort of one option you have. I mean, Leland earlier mentioned dimensionality reduction, right? Like, sort of as another approach, right? Like, as long as there's, in particular, when these vectors are larger, there may be sort of redundancy in there, or there may be like essentially sort of like a trade-off between, like how much space are you using, and sort of what is the granularity of the semantics that these representations are capturing, right? Like through their pairwise distances. And so what you can try and do is essentially approximate the embeddings that you have by embeddings that are smaller, either through quantizing them, right? So using fewer bits per number, or like chopping them up in some way, and then sort of quantizing those parts, or by just sort of reducing the number of numbers, which is what dimension reduction is doing. And you pay a little bit of a price in terms of utility, right? Because you lose some granularity in the representation that you use for the search. But if you gain a lot in terms of query performance, then that may be a great trade-off to use, right? And that's, I think, sort of where an example of like the type of tuning that Leonard was talking about that really influences sort of what is the practical performance that you get out of these systems, both in terms of utility and speed.
So I'm going to go out on a limb, and I like to reduce things to like simple mental models that I can deal with. And in my mind, there are actually only two effective methods for approximate nearest neighbor search for high dimensional vectors right now. And one of them is compression, which the quantization techniques fall in that category. It's all about managing to squeeze the data down so that it's smaller and faster to search. And so that's very effective. Exactly the techniques required to allow you to squeeze it down and still retain enough information to do search well, that's very complicated. And that's where all the different versions of different algorithms come in. And the other approach, instead of trying to squeeze the data down, is to sort of essentially believe that the data exists on some lower dimensional intrinsic structure that's maybe nonlinear. And these are the graph-based techniques. So there you construct a graph from the data, and you basically search by walking through the graph. And all the different techniques to do this have different ways to construct the graph, different ways to prune edges and make things run faster. And so you get a lot of different algorithms, but they're all really build a graph and search through the graph. So I believe there's compression, and that's where all your quantization techniques, product quantization, and all of these sorts of methods fall. And then there's the graph-based, and that's where you've got HNSW and a bunch of other techniques are all in that category. And that's a distinct trade-off you want to be careful of. There are two very distinct approaches, and they both have different pros and cons to them. So if you are doing a compression-based one, your index is going to be much smaller in memory, and that's going to be good if you want to search very, very, very large volumes of data. But you can get better recall per query time trade-off with the graph-based techniques. It just doesn't scale up to the really large data sets quite as well. There are now some efforts to sort of combine a little column A and a little column B and do some graph-based search of compression techniques, but I think that's still in the works. I haven't seen anything that I would call a wrapped, polished solution for that yet, but maybe others here have seen more on that.
Leland, one question for you. So a lot of people in the audience here, they might be technical. They might know like this idea of a graph from like some undergraduate course. But like when you say graph here, what precisely do you mean? Like what are the nodes? What are the edges?
Right. So what we're doing here is constructing a k-nearest neighbor graph, essentially, and then pruning edges. So nodes are your data points, and edges are basically just links between those data points.
The data point, you mean like an embedding, right?
Yeah, yep. We're working from the embedding. So nodes are the embedding vectors, and edges are just connections between embedding vectors that are close for some measure of close. And this is, you can think of it as trying to approximate some structure that's lower dimensional that the data lives on, and you're traversing that structure rather than having to search through the whole data set.
Awesome.
So on a practical level, so the different applications where you might be considering these. So for example, a recommendation system would have different considerations than Facebook's post search versus an LLM, where the LLM you want really good semantic subtlety, nuance, whereas a recommendation system can be more coarse. Those are the kind of different examples where I guess I'm saying, but I'm also asking, depending on, those are examples of different use cases where these different considerations will be weighed differently. Yeah, cool. Someone in chat mentioned hierarchical navigable small worlds, HNSW, as an acronym for...
I think they were just clarifying the act. Somebody said HNSW and then they linked.
Oh, okay, great. Yes. Cool. I think that one flew past me.
Acronym.
So that's I'm realizing now we kind of, when we were preparing for this, I kind of had vector databases and vector search separated topically, but they're really tightly related. So we've already talked quite a bit about vector search. I want to talk a bit about the actual the mechanisms of the vector search. So my understanding, based upon prior understanding and from the event here, is that basically you can, if you do a literal distance measurement, you have say 1,000 1,000 elements, and you can calculate that distance exactly. But as soon as you start saying, well, let's see if we can not worry about some of those, and you do dimensional reduction or different spaces, it sounds like then you're faced with a nonlinear optimization problem. Is that accurate? Or am I off in left field?
I'm gonna go on a whim here and say it's a little bit inaccurate.
Okay.
The core problem. So the reason why you have like approximate nearest neighbor search algorithms in the first place is to get away from this whole computation that you have to do. So like in the ideal world, right? So let's say you have like 1 billion embeddings, right? In the ideal world, I can go in and for every embedding to every other embedding, I can compute the distance and I can store that distance, right? And then anytime I need to go and I say like, oh, how far is like the embedding of my dog from the embedding of like your dog, I can go in and just retrieve that distance from each other, and then maybe I can rank those distances and give you like a list out like you would get in like a Facebook feed or like Google. But the problem is that if I have 1 billion, like pieces of text or billion pictures, if I keep going with my dog example, that's actually a pretty intractable computation to do because it scales quadratically with the number of data points. I add a new data point, and my marginal computation I have to do now is like 1 billion more computations. So the whole principle behind approximate nearest neighbor search is you can do that a lot faster by not having to compute the sort of inner products between all possible points, the similarity score between all possible points, and you can approximate a little bit. And sort of how you do that approximation is sort of like the tuning that we were talking about earlier. Yep.
Might be worth briefly covering some history of nearest neighbor search because the old school approach to this was tree based, where you would progressively carve up the space into finer and finer leaves of a tree. So that provides exact nearest neighbor search, and it's very, very fast. And it's great, especially in low dimensional spaces. But now that we ended up with all these embedding vectors that are, as Lauren said, into the thousands of dimensions, it's very hard to apply those techniques because they scale exponentially in dimension in terms of complexity, how hard it is to do this. So effectively, they're no better than brute force search for high dimensional data. And so this is the challenge. And so the algorithms we had stopped working for these kind of high dimensional problems. And so people decided, well, we're going to have to give up something. And so what we gave up was exact search. So you can either make the distances a little bit more approximate. So you're approximating the distance. That's essentially how the compression and quantization based techniques work. You're not calculating the true distance between these things, just an approximate one. And so your ranking of which are the closest things are not going to be entirely accurate. Or you can accept that you might not find all the nearest neighbors because of just the way you set up your index. They're just not going to fall in your search, but you'll just find as many close ones as you can and do a decent job that way. And that tends to be the trade-off that the graph-based techniques use. So you've got to give up something to manage to make this tractable in high dimensions, and that's where the approximate search comes in, and that's where you're having to decide what trade-offs to make, what things to give up to do that, and that tends to decide which algorithms are most effective for this for your use case.
Yep. Brian, I think we should move on to discussing visualization here, as like this is the thing that the audience here, like the panelists rather here are sort of the experts at. Do you mind if I sort of kick it off, and then I want to just give it away to Lawrence and Leland. But basically, like what we do at Nomic is we work on sort of productionizing and sort of like making sort of like available to everyone to use the sort of algorithms that Leland and Lauren sort of spent a lot of their lives sort of like developing and building on. So I think what would be really useful for everyone. It's like a lot of people, like, they don't understand why one would even need to like visualize an embedding space, or just like giving some clarity to the world of just like, why is this a useful operation, and like what kinds of things you can learn about your data or even about your embeddings, just basically like to help, like, understand what your neural network is doing by visualizing embeddings. And maybe some history, just like, I think the world would love to hear, just like, Lawrence and Leland, why did you guys start working on these problems in the first place even? Yeah.
I guess I'll start a little bit. So why would visualization be useful? I tend to think of this in terms of if you talk about vector databases, people talk about doing queries, and everything is query focused. And what you're doing there is having a specific starting point and getting out some specific small set of answers. And that tells you a very small amount about your data, based on maybe a well-chosen query, but you're looking at your data through a straw. You're looking through a very narrow pipe at a very small amount of data. Maybe you could think of it as like a little tiny narrow flashlight, pen light, looking in a dark room. You can see a little bit. And so what these visualization techniques try to do is manage to look at all of the data. Now, you're going to have to make sacrifices to do that, but it is a way to look at the whole rather than individual bits and pieces. So that's my notion of why these things are important. You can see the things that you didn't even know you were supposed to be looking for. So the unknown unknowns in your data, those are really important, and you'll never find them if you're working in a query-based mold of how to look for things.
And visualization requires, roughly speaking, a dimensionality reduction that's of a piece with what you were talking about with the storage approaches, just much further down to, a few that you can actually render on a page or a screen.
Yeah, very much so. And I think rather than the quantization techniques, you really want to use something that can understand nonlinear structure in the data. And I think that's where these sort of more recent advances, and I say more recent in terms of like the long history of dimension reduction, which extends back to the 1910s. More recent advances have really brought out, and I think TSNE, which Lauren's built, is really the breakthrough advance that sort of made everyone realize this is really powerful for actually doing visualization. This can actually reveal real interesting structure in a way that previous techniques just hadn't been able to do. So I think, that's where this all really started, is those sorts of approaches and what they can show you about your data that you would not otherwise be able to see.
TSNE.
Yeah.
Go ahead, Andre.
I always get is like whenever anyone hears like, dimensionality reduction or like visualization of embeddings, they usually mean like, oh, you're putting in some sort of like human interpretable view. But everyone, when people think dimensionality reduction, they think like SVD or some sort of like some sort of like linear algebraic based approach for distilling out essence from like your matrix of embeddings or something like this. How do these like algorithms that like TSNE or UMAP sort of differ from these sort of more like traditional approaches for actually doing dimensionality reduction of like large matrices, for example?
So I think the key difference, I mean, as Leland already described, is sort of in the non-linearity of these newer techniques, right? So if you're using techniques like SVD or principal component analysis, which are sort of like the classic statistical tools for reducing the dimensionality of your vectors or embeddings, like essentially you're really limited in terms of like how you compress things down. You basically like you have this massive space and you sort of like can only look at a tiny slice. And so like as a result, like those tools are very useful, for sort of compression type use cases. Like they're pretty usable. but they never really give you visualizations that lead to good results or that lead to insights of like, oh, now I have a sense of what my data looks like. The second thing is they sort of optimize for the wrong thing. So like what techniques like SVD or PCA are very concerned about is making sure that if I have two embeddings that are very different, that those are like sort of the right amount of different in your visualization. And if as a human, you look at a visualization, so something like a scatter plot or something, sort of the way that our human perception works is we look at things that are nearby, right? Like, oh, here's this like gene measurement that I did, or this photo that I took. What are like similar things to it, right? Like that is literally what sort of vector search in vector databases, which we talked about earlier, is trying to do. And when you look at visualizations, your sort of like human brain looks at it that way as well, right? And so what techniques like TSNE or UMAP are doing is they're trying to make sure that in a visualization that you create, that similar embeddings in sort of the underlying data are captured by similar or nearby sort of low dimensional points in your visualization. And as a result, they give you a much better sense of sort of like what your overall data looks like.
Yeah, at the very beginning of this panel, Leland mentioned the phrase like relative distances, and embeddings and understanding embeddings and working about it with embeddings is all about this concept of relative distances. And it's exactly what the techniques you guys built like do. They preserve relative distances as opposed to preserving other types of structure.
Like one of what I'm hearing, and correct me if I'm wrong, the SVD, those methods are linear, and in traditional ANOVA and statistical analyses, they need to be, you want linear because the methods you're using call for linearity in your reduction, if I understand it correctly. Whereas human perception, semantic connections are intrinsically nonlinear, so it then makes sense to me that your reduction, your processing would also need to be nonlinear in order to at least more substantially or more accurately represent the reality.
Well, and your data is likely sort of nonlinear as well, right? Like if you sort of think about like this really high dimensional space, like say this 1,000-dimensional space where all these embeddings live, right? Like, sort of these embeddings are sort of points that are, scattered around this space, right? And what you say when you use PCA to do dimension reduction to, let's say, 2 or 3 dimension is you're essentially saying like, oh, I can find a like 2-dimensional plane that I just sort of like fit in this space, and then all the points lie on that plane, right? And that's sort of like what if the data was like linear, sort of had a low dimensional linear structure, like that would be true. And then your PCA visualization would be amazing. It would capture all the structure in the high dimensional data. But that's not what real data looks like at all, because real data was created by very complex processes that we often hardly understand. That's why we're looking at this data in the first place. And so it can create like the data points will lie on all sorts of like weird curves and so on. And then they're in high dimensional space, which we don't even intuitively understand very well anyway. And so like that sort of the model of data that PCA or SVD assumes is just very unlikely to be the right model for sort of any real world data set out there.
So like putting it in 3 dimensions, it's almost like say the relevant part of the data set is the shape of a banana, and that you have a couple of points at either tip of the banana, and then PCA would take a plane that would cut the 2 tips of the banana, and then you'd have some points that are in the middle of the banana, but they get projected onto that plane, and then the projection then puts them outside of the original banana.
Yeah, I mean the I guess sort of example that people use a lot is more of like a Swiss roll, like sort of type structure, right? So like if you sort of like imagine like a sort of a curved Swiss roll, or like some other pick your favorite pastry, right? And now you like stick sort of a 2-dimensional plane in it, and then you squash your pastry onto that plane. now you don't have an accurate representation of like, like which parts of the pastry were close to each other in the original
Originally.
thing, right?
So
And that's just
unroll.
going from like a 3D to a 2D thing.
Mhm.
We're going from 1000D to a
Yeah.
2D thing. So the problems are exponentially worse.
Got it. Yeah. So then, in the Swiss roll example, you might, if you cut that plane, you might measure 2 points as being close together, when in fact, if you unrolled the pastry, they were actually far apart.
Correct. Correct.
Understood. Got it. Got it. Got it.
Yeah, I think you want to think about it as following regions of density within the data, and for the Swiss roll, that's following it around the spiral. There's distances that cut across, but you want to follow where the density of data lies. And in high dimensions, this happens all the time. And density varies very weirdly in high dimensional spaces. Again, this comes back to, even if you think you have good intuition for high dimensional spaces, you don't. It always just breaks your brain in ways you don't expect. So I think, there's a lot of value in trying to just find ways to follow the data as it sort of folds itself through this space. And so I talked about, relative distances. I like to think of that in terms of topology. That's a study that cares about relative distances and things like that. And so for me, these embeddings, the important thing is the topology of the data in the embedding space. And so going back to what I talked about at the start about different numerical representations that have the same relative relationships, this topology might be the same for embeddings, word embeddings of English and word embeddings of Spanish that are otherwise incomparable to each other. It might be possible that the topological structure, the geometry of how the words in this language embed have some similarities. And so that's the sort of thing that you can see on the whole with visualization that you're not going to see by querying individual data points, is the overall structure, which is really what's in many ways important about the embedding space, is how all these things fit together relative to each other.
Nice. One thing I'll add here is so I know Ben here in this panel, so like that's really great, like research background and everything. One thing is like once you have that actual layout, so like you produce your sort of like two-dimensional view of your high-dimensional data set, you've preserved all those like those really nice relative distances. One thing Ben is sort of has expertise in here, which is actually really hard once you try it, is actually showing that on a computer nowadays. And like if you can't do that, it's not really useful for larger data sets larger than about 100,000 data points. So maybe Ben can say some stuff here at the end too, as we're approaching time.
Yeah, and I think that something that unites what Andre is talking about, what Willem was just talking about, is that one of the ways that we learn how to think about these spaces is by borrowing a lot from like cartography. I think a lot about cartography, and both in the sense of dimensionality reduction, because map projections are like the first place where people had to figure out how to squash a three-dimensional shape down into 2 dimensions. And those reflect choices that people make about how to structure that high dimensional data. Like in American maps, like when I was a kid, you would still see like the world split in the middle of India and Russia all the time. When I made maps of Wales, Wales, not the country, the animal, you have to make different choices about like, you want to keep oceans contiguous versus countries contiguous. And those are the sorts of choices that are made in these algorithms. And often what the things like these nonlinear algorithms do, the way I think about it, is like when you get one of those tourist maps at a rest station that shows the downtown in incredibly high precision with all of the stores stretched out, and then it takes that sort of New Yorker view of the universe where like you get a road that is not to scale, but that shows you all of the things you might want to do on that road as you go. Like that's what's actually useful for human beings in navigating these kinds of spaces where they need to know what the points are and what they want to do with them. And that's what these nonlinear methods can be really good at. And that's sort of old school cartography. And then new school cartography is like figuring out how to work with like data formats that actually send lots of things over the wire and that let people explore these interactively. And this is like I don't know, I'm sort of curious from Leland and Lauren's perspective, actually, like what the stuff that you would like to see next in ways of interacting with or understanding these high dimensional data sets is, because I think we've gotten pretty good at two-dimensional reductions, but the sort of operations that we find people often wanting to do, or to like emphasize some parts of this to stretch the high-dimensional data set that you're looking at in different ways. There's an old video of John Tukey, like the godfather of exploratory data analysis, that I don't see a broadcast channel for, but I'll put it on my Twitter or something so people can find me afterwards and look at it. That's like creating the machines where you like look around at the high-dimensional data sets. And I'm curious if you see like new frontiers for helping people understand these things better going forward.
I mean, I think the key there is not so much maybe on the like dimension reduction algorithmic side, but really on the interaction side. And that's where I'm really excited about some of the stuff that you have been building, Ben, and that the folks at Nomic are building more generally. I mentioned this to Andre when we spoke earlier, but like when I worked on TSNE myself, which was back in like 2007, 2008, like we actually had a lot of the vision that I think Nomic is implementing right now. We kind of had that like as a motivation in our head, like, hey, it'd be really cool if you could like make a massive map of your data and then sort of like zoom in and select some piece and maybe use it for labeling and sort of like do further inspection. And these things are also like these types of like cycles are also formalized in things like visual analytics and so on, sort of folks in the visualization community who've thought about that quite deeply, sort of what the process there would be. And the thing that was missing was essentially like JavaScript was crap. And now it's not, right? And I think, well, you know, it's not perfect, but it's in a lot better shape than where it was in 2008. And that's really, I think, enabled some really cool sort of new products that build on top of these core algorithms. And I think that's exactly sort of the space where Nomic is operating.
Yeah, I want to throw in, I think interactivity in these visualizations is the critical piece. Like that's what really brings it to life for a user to be able to find insights out of it, is being able to actually interact with it, get back to the source data, find what data is relevant, search through the data and show different things within the visualization, zoom, pan, all these sorts of things. That interactivity just really brings a lot of value to the whole thing. It kind of is what seals the deal, makes it actually work as a thing. And certainly, you know, Nomic is an example where you've built a system that can scale to billions of data points, which is really impressive for being able to actually explore these truly vast data sets, which I just don't think has been remotely possible up until now, not to explore it in the holistic way that these sorts of visualizations provide.
Excellent. Well, we passed, I'm not muted, good. We passed the top of the, or bottom of the hour. We probably should wrap up. Thank you, Leland, Andre, Ben, Lawrence. Really appreciate your time and your input and insights here. I learned a lot. Thank you for correcting correcting my misunderstandings. Thank you to everyone who attended. As I said at the top, we are recording the event and the video will go up soon on the OpenTeams YouTube channel. Again, you can subscribe there to get a notification when that's posted. Check out all of our panelists on social media and check out openteams.com to learn more about us and our offerings. And we'll see you next time. Thank you very much. Have a good one.